Yes, welcome back. Last time we talked about one of the most important concepts in data analysis, attribute types. Attribute types tell us what the data actually represents, and just as importantly, what we are allowed to do with it. This is fundamental to doing correct data analysis. Let's quickly recap the key ideas. Nominal attributes answer the question, what kind? They simply place data into categories with no notion of order. Ordinal attributes answer what order. They allow us to rank values, but we still don't know how big the differences are between them. Interval attributes go a step further. They answer how much difference. Now, the differences between values are meaningful, but we still can't talk about ratios. And finally, ratio attributes answer how many times. Because they have a true zero, both differences are and ratios make sense. And here's the critical takeaway. If you use the wrong operation on an attribute type, your results become meaningless. You shouldn't average nominal data and you shouldn't compute ratios on interval data. Always let the attribute type guide your analysis. So, as we move forward, always keep this in mind. The type of attribute determines what you are allowed to do with the data. Make sense? Now let's look at what determines the type of attribute. It all comes down to which properties and operations it possesses. There are four key properties we look for, each building on the last. First, distinctness. Can we say two values are equal or not equal? This gives us the operation equal or not equal. Every attribute type has this property. We always need to distinguish whether values are the same or different, right? Second, order. Can we arrange values in sequence? This gives us the comparison operations, less than or equal, greater than or equal. Some attributes have this, some don't. Third, meaningful differences. Can we add and subtract values in a way that makes sense? This gives us addition and subtraction operations. This is, a more advanced property compared to the distinctness. Fourth, meaningful ratio. Can we multiply and divide values in a way that makes sense? This gives us multiplication and division operations. This is the most advanced property. And here's how these properties maps to our four attribute types. Sorry. Nominal attributes, or nominal attribute has only distinctness, okay? The two eye colors are equal or not equal, but you cannot order them or do math on both or on them, right? An ordinal attribute has distinctness and order. So you can rank items, but you cannot say how much difference exists between ranks. Interval attributes has distinctness, order, and meaningful differences. You can add and subtract. The difference between 20-degree and 30-degree is meaningful, but you cannot form meaningful ratios. Ratio or ratio attribute has all four properties: distinctness, order, meaningful differences, and meaningful ratios. You can multiply and divide. 20 seconds really is twice as long as 10 seconds. Yes. So the key insight here, each attribute type builds on the previous one, adding a new capability. The properties determine what you can legitimately do with your data. And this is, summarize everything, guys. Okay. So let's think about this question carefully. Is it physically meaningful to say that a temperature of 10 degrees is twice that of 5? It should be twice that 5 degree, right? I know what's not on here, so I will fix it here. So it's physically meaningful to say that a temperature of 10 degrees is twice 5 degrees. Think about it for Celsius, Fahrenheit, and Kelvin. Okay? Pause for 1 minute, then resume the video. So, well, depends on scale you are using, right? So take a look first. On the Celsius scale, the answer is no, right? We agree, right? We got the same answer. Zero doesn't mean no temperature here. It's just an arbitrary reference point. So saying 10 Celsius is twice as hot as 5 Celsius doesn't actually make sense here, right? Same thing applies to the Fahrenheit scale. Again, zero is arbitrary, so ratios like twice as hot are meaningless here as well, right? So hopefully we got the same answer so far. But the Kelvin has a true zero, absolute zero, where thermal energy is essentially minimal, right? So because of that, ratios do make sense here. So in Kelvin, saying 10 Kelvin is twice 5 Kelvin is physically meaningful. This example highlights an important idea. Only ratio attributes support meaningful ratios. Interval scales like Celsius and Fahrenheit do not. Make sense, guys? Good. This slide summarized the previous one perfectly, okay? So you can see how each attribute type inherits, let's say, properties. Nominal only, let's say, has distinctness, okay? Ordinal adds order, right? Interval adds meaningful differences, and ratio adds meaningful ratios. This hierarchy is fundamental. Always ask yourself, what operations are valid for the attribute I'm working with? This will guide your analysis. Okay. Um, I think, yeah, let me share this. I'm gonna maybe allow here. I'm going to talk about the quantitative attributes and qualitative attributes. Okay. Let me say these attributes. Mhm. So what quantitative attributes? Here is defined as attributes that represent, let's say, numeric quantities and can be measured on the numerical scale. So again, it's attribute that represent numeric quantities and can be measured on a numerical scale. You can perform arithmetic operations. Here you can do addition, you can do subtraction, I can do addition, I could do subtraction, I can do multiplication, I can do division. All right. And statistical analysis, I can do mean here, I can do variance, for example, etc. All right, correlations, etc. Examples here for the quantitative, you can say we have, for example, age in years. You can say there'll be salary in dollar or whatever. You can say height. You can say, for example, the temperature, etc. Okay? It's subtypes. It can be, let's say, continuous or discrete. And it can be, let's say, discrete here. Seeing that internet disconnected, but it's great. Continuous, that means in this case, measurable along a range like height or weight. In other words, can take any value in a range. You can say take any value in a range. Okay. Discrete is countable like numbers of students. So in this case, take distinct values. You take distinct. Okay. After integers, for example, number of children, number of the student, for example, or let's say number of transactions. Yes. Okay. So, for example, if you have number of books, for example, in a library, we call this one discrete. If you have height of the student, continuous. Temperature in Celsius is continuous. Number of cars passing your street in an hour is going to be what? Discrete, right? Okay, back to the qualitative here. Quantitative, that means in this case, attributes that describe categories or qualities rather than numeric measurement. So here it's going to be to say categories, maybe, or let's say I've said qualities. Okay. So you can classify here, you can do counting, you can group them, but you cannot perform arithmetic operations. So arithmetic operations don't make sense. Operations, they say, don't make sense here. Okay. Example, for example, eye color, right? Either can have, for example, few values, I mean, set of values that choose from. You can say blue. It can be, for example, brown, black, and etc. Right? Customer type, for example. Okay. It can be, for example, regular or BIB customer, right? Product categories, for example, it can be electronics, clothing, books, whatever. It has, I mean, subtypes. Either gonna have something say nominal here, or gonna be ordinal. Okay, nominal that means no inherent order, right? For example, color, genders. There is no order here. Ordinal can be ordered categories. That means in this case, maybe you have rating. For example, maybe you're gonna have, for example, poor, and maybe you can say average, or let's say excellent. Let's write this one again. So you have three to say categories that you can choose from, and it has order here. Okay, good. Let's see this exercise. Okay. For each attribute below, determine whether it's nominal, ordinal, interval, or ratio. Okay. Pause the video, then try to find an answer. And we're going to talk about this one maybe next lecture. Okay. Yeah, we're done with this part. Yeah. Good. Yes. Now let's look at another way to describe attributes. And here, by the number of values they can take. Okay? This gives us the distinction between discrete and continuous attributes. A discrete attribute has only a finite, or to say, countable infinite set of values. Okay? That means you can list the possible values even if the list is extremely long. It's still countable. That's what we said here. Discrete attributes can be either categorical or numeric. For example, zip codes are discrete. Okay, there is a fixed set of possible zip codes. Counts are discrete. You can have 1, 2, 3 items, but not 2.5 items, especially with a count. You cannot say we have 2.5 students in this class, right? The set of words is a collection of documents, is discrete as well. Each word is distinct entity. Discrete attributes are often represented as integer variables in programming and data analysis. Okay, it's worth mentioning here, or worth noting that binary attributes, those that can take only two values, like a true, false, or yes, no, are a special case of discrete attributes. Okay, now Continuous attribute has real numbers as attribute values. These attributes can take on any value within a specific range. Example includes, say, temperature. It can be 20 degree, 20.1, 20.01, and so on, right? Height, there is an infinite number of possible heights between any two measurements, right? Weight, similarly, can be measured with increased precision, right? However, there is an important practical consideration. Real values can only be measured and presented using a finite number of digits. Okay? In practice, we always round or limit precision, but conceptually, the attribute itself is continuous. And computing, continuous attributes are typically represented as floating point variables. The key distinction here, right? Discrete attributes have gaps between possible values. Continuous attributes do not. Typically, nominal and ordinal attributes are binary or discrete, while interval and ratio attributes are continuous. However, count attributes, which are discrete, are also ratio attributes. Okay? Now let's explore let's say a special type of attribute called asymmetric attributes. The key idea with asymmetric attributes is only presence, a non-zero attribute value is regarded as important. Absence or zero values carry no meaningful information. Okay, I think I can have this example. Oh, yeah, let me switch to the tablet so we can talk about that example here. So let's have a concrete example. As I said, imagine a university data set where each object is the student. So assume that we have a student here. Okay, let's have a table like this. I'm not gonna do everything, but assume that. Okay, so assume that we have Alice here, for example, we have a Bob. Okay, let's good. And each attribute records whether or not student took a particular course. Okay, for a specific student, an attribute has a value of 1 if they took that course and 0 otherwise. Make sense? So assume that we have CS course CS 100, CS 201, CS, for example, 425, and etc. I'm going to list all the courses here. And for each student, you have to record the following, whether the student take this class or not, or took that class or not. For example, Alice took these classes, they didn't took the rest. For the student took all these classes and not all of them. So we have zeros and ones, right? Either it can be 0 or 1. And we have to list all the courses. Assume that we end up, we have how many courses we're going to offer. It depends on the university. I'm going to say, for example, 1042 possible course, maybe. That's just an example, okay? So now, there is a critical point. Students take only a small fraction of all available courses, right? Because in the university, we do have like a different departments. And each department going to offer their courses, right? For example, computer science student or computer science student class, or I mean, computer science student is not going to take every single course offered by the other departments, right? So in this case, again, we're going to see that student takes only a small fraction of all available courses. At a typical university, there might be 1,000 of courses, but a student takes, to say, only 30 to 40 in their entire degree. That means most of the values of the set, over 98% here from the data that we have here, 95% gonna be zeros. Right? So what happens if we treat zeros as meaningful? So that means in this case, if we compare students based on the courses they do not take, then most students would seem very similar, right? They all didn't take almost the same thousands of courses. This similarity is meaningless and misleading. This is why we focus on the non-zero values. the courses students actually took. It's more meaningful and more efficient, right? Other common examples might be, for example, words present in documents. When you analyze, for example, a text, we care about what words to say actually appear. The fact that a document doesn't contain thousands of possible words tell us nothing interesting, right? Items to say present in customer transaction. When analyzing shopping behavior, we focus on what customer actually bought. The items they didn't buy aren't mean, right? I don't care what you didn't buy. I care what you actually bought, right? Back to the slides. Sorry. So here's a thoughtful experiment that perfectly illustrates this concept. If we met a friend in the grocery store, right? Would we ever say, "Oh, I see your purchases are very similar since we didn't buy most of the same things"? No, of course not. That would be absurd, right? Similarity, okay, comes from what you did buy, right? Not what you did not. Binary attributes where only non-zero, okay, values are important, okay, are called asymmetric binary attributes, and they require special treatment in analysis. Now we have covered the classic categorization of attributes: nominal, ordinal, interval, ratio, discrete, continuous, and asymmetric. It's important to acknowledge that this knowledge or this framework, sorry, has limitation, right? Let's explore some critiques. First, the traditional categorization is incomplete. Real-world data includes many situations that don't fit neatly into these categories. Okay, so asymmetric binary attributes we already discussed. Okay, they require special treatment. Cyclic attributes, okay, like days of the week, months, or directions, where after Sunday comes Monday and after December comes January. There is no true beginning or end, right? Multivariate attributes, where one conceptual attribute is actually composed of multiple values. Partially ordered attributes, where some items, okay, can be compared but not all, like a family tree, where you can compare across generations, but not within the same generation. Partial membership, okay, where something can belong to multiple categories to different degrees, okay, like fuzzy logic. And we do have the relationships between the data. Attributes don't exist in isolation, they interact. And second, and perhaps more critically, real data is approximate and noisy. In theory, we can classify attributes to say perfectly. In practice, measurement has, or say, have error, data is missing, values are rounded or to say approximated, there's uncertainty and imprecision, right? And this noise can complicate, to say, the recognition of the proper attribute type. Is that temperature reading interval or ratio? Well, if the thermometer, for example, is slightly miscalibrated, does it matter? Sometimes yes, sometimes no. Right? So this leads to a practical challenge. But treating one attribute type as another may be approximately correct, but can also lead to inaccuracies in analysis and interpretation. Okay? For example, treating ordinal data as interval, assigning number 1 to 5, for example, numbers 1 to 5 to survey responses, and averaging them is common practice. But technically, we cannot guarantee the psychological distance between agree and strongly agree is the same as between neutral and agree, right? Treating noisy interval data as ratio might be fine or might introduce subtle bias. The key takeaway: these categorizations are guides, okay, not rigid rules. Always consider the nature of your data, the measurement process, and the practical, let's say, context of your analysis. Okay, that's going to be summarized here. Good. Now that we have explored attribute types, okay, let's look at how they come together in data sets, okay? We can go by data set into three broad categories: record data, familiar tabular format, graph-based data, which capture the relationships between entities, and order data where sequence matters, like time series. Okay, these categories, okay, they are not to say aren't exhaustive. Okay, you will also say encounter text, multimedia, streaming, and sensor data. So different grouping are possible depending on the characteristics you focus on. The key point here, understanding your dataset type helps you choose the right tools, the processing steps, and algorithms for analysis. Okay, so we have talked about dataset type, right? Now, let's look at the four characteristics that really shape how we work with the data. First, dimensionality. This one is simple. It's just how many attributes we have. Low dimensionality might be 10 attributes, high dimensionality 10,000 or more. And here's why it's magic. When, okay, dimensions get high, we run into what is called the curse of dimensionality. We got to look at this one later. So in general, data gets sparse, distance between points stop meaning much, and suddenly your computer is struggling to keep up. Sparsity, this is when most of your values are zero, okay? Think market basket data, thousands of products in the store, but the customer only buys 5 or 6 items. Over 95 or 99% zeros, okay? So in cases like this, we only care about the non-zero values, okay? Sound familiar? Yes, it's the same idea as asymmetric attributes, just at the dataset level. The solutions is about the level of detail. And here's the key insight. Patterns, okay, it changes depending on how zoomed in you are. Okay, in other words, patterns change depends on how zoomed in you are. Temperature by minutes, for example, look completely different from temperature by the month. Stock price by the second versus the year, right? So pick the wrong resolution and you might miss the pattern entirely. Or worse, find one that isn't really there. Finally, the size. Obvious, right? I'm talking about the size of the data set, right? But worth stating, 100 tuples and 100 million tuples or rows need completely different approaches or techniques. We need to handle them differently, right? Different size. Some algorithms, you say, or algorithms, you say, scale perfectly, others just crash. So the size affects everything. The storage, memory, processing time, even which statistical tests that you can use. Okay? So these four characteristics, dimensionality, sparsity, resolution size, they are not just academic. They tell you which tools to reach for, how to clean your data, and what you can actually believe in your result. Okay? Well, we're gonna talk too much this lecture and the next lecture, but hopefully in the future we're gonna have like some practice. We're gonna see how can we, for example, use Python in order to try to perform do some programming and we can start to visualize our data that we have. Right now, still we need just to build our bases, okay? Now let's look at the three main categories of data sets you will run into. Okay? Record data. Okay, this is your familiar tuples, rows, and columns format. Excel sheets, database tables. Okay, pretty straightforward. But within record data, you have got a few subtypes to say worth knowing. Okay, we have a data matrix. Okay, just your standard numeric table. We have a document data, which can be text documents as tuples and rows. Words can be as a columns, as we're going to see later. Transaction data, here in this case, like market basket, one tuple per purchase all the items bought. Next, graph data. This one's about relationships, generally. We have got nodes, which your entities and edges, the connections between them. Two classical examples. The World Wide Web, okay, which in this case you have the web pages are nodes and the hyperlinks are edges, the connection between them. Okay, molecular structures, okay, atoms are nodes, chemical bonds are edges. So if your data is about who's connected to what, you are in graph territory. Again, if your data is about who's connected to what, you are in graph territory. Okay? And we have finally the order data here. Here, sequence matters. This covers a lot of ground. Spatial data like GPS coordinate. We have temporal data, time series, stock price, sensor readings, sequential data, for example, text, speech, order matters in general, right? Genetic sequence data, for example, DNA, where the sequence is the whole point. So that's the big three, okay? Record, graph, ordered. We'll figure out which one fits your data, and you are already on the right track of choosing your analytical approach. Let's start, I'll dive deeper into these types of data. We'll start with the record data. Okay? We start with that one because it's easy, right? It's the one you will see most often in general and easy to work with. So, record data is simple, collection of records, as you're going to see here, okay? And each has the same set of attributes. So each record has the same set of attributes here, okay? Think of it as a table, as you said, if you're going to be different records here, a person, a transaction, an object, okay? Every column is going to be an attribute describing that record, okay? So this structure is everywhere, customer databases actually sales transactions, patient health records, survey response, and etc. All of these record data. Okay? The magic is on the consistency here. So we talk about why it's going to be powerful. Actually, the magic here is in the consistency. Same attributes for every record. That means we can compare across records. You see, easily, we can apply standard statistical methods, and we can build predictive models without jumping through hoops. Okay. This tabular structure is the foundation for the specific variations, okay, we are about to look at, okay? The data matrix, the document data, the transaction data, they are all built on the same tuples, rows, and columns idea, okay? So let's jump to the next now. All right, so let's look at the data matrix. The matrix first, the flavor of the record data. Okay. So a data matrix is what? It's just record data, okay, where all the attributes are numeric. Make sure all the attributes here is going to be numeric. That's it. But here's the cool part. Once everything is numbers, we can think of each record as a point in multi-dimensional space, right? And the whole data set becomes a matrix we can use with linear algebra. Okay, so the first point here says the same thing more formally. If every object has the same fixed set of numeric attributes, we can think of them as points or vectors in multi-dimensional space. Each dimension is a different attribute, or different attribute, sorry. This first part, right, that explains everything, hopefully. Good. So a person or test, or let's say a transaction, whatever is it, okay, becomes a vector and you say n of numbers, right? And the whole data set becomes a matrix. So let's walk you through to say what these numbers actually mean. I'm talking about what we have here in this example. So assume that we're gonna have what? It's going to say material testing example. We have got, 4 tests, okay? 1, 2, 3, 4 tests, okay? And that's gonna be, we have m tuples or m rows here, and 1 pair object, okay? And 5 attributes, 1, 2, 3, 4, 5 attributes. Each of them has a specific meaning, okay, for the material test. So test 1 can be right as a vector, okay? 10, 23, 5.27, 15, 0.22, 27, 1.2, and etc. Okay. Okay. So again, and now, as I've said, here's why this setup is powerful. Why is it interesting? Okay? Because we have got a proper matrix. Since we have a matrix, we can apply standard matrix operations. I can do transformations, I can do projections, I can do multiplications. All the linear algebra tools are now on the table. And That's exactly why the data matrix is the standard format for the most statistical data. Okay, regression, clustering, PCA, as you're going to see, they all start there. So I'm not gonna continue. As that hopefully that makes sense. So later when we talk about this one in details, we're gonna have maybe more. I mean, we gotta look at this one. We still just introduce what type of data that we have, or data sets. Okay. This way, next up is gonna be the document data. Okay. Um, special type of record data. Okay, we still have a record data. Here that each document is gonna be the same record. Assume that we have this example, we have 1, 2, 3 documents. Each record or each tuple or each row or each document can be represented as a record. A record might be, for example, anything. It might be an email. It might be, in this case, a news articles. It might be tweet, whatever. Okay. And the attributes here, okay, they are the words that appear in those documents. Here, for example, team, coach, play, ball, score, etc. All these words get that appears on those documents. Okay. So if we have, to say, 1,000 documents and 10,000, say, unique words across all of them, you have got a matrix with 1,000 tuples, rows, and 10,000 of columns, right? Okay. And what's going to have or goes in each cell here? And it's going to end up, we have the matrix, right? We have number of documents, and here the words that appears in those documents. So what the actual value can be stored here? So it's the count or frequency of that word in that document. In other words, how many times does the team word, okay, show up in this article? How many times the team word shows in the document too, and etc. And continue to coach here, for example. It appears 7 times that document, and etc. Okay, so that number goes in the cell. So the question is, why does this matter? Why is it interesting to look at this data set? This format lets us doing things like find, to say, similar documents, for example. They have similar word pattern. For example, look at the document, they have the same, I mean, the subset, I mean, to say, the same, to say, word patterns in general. Classify, for example, emails as spam or not spam. Identify, for example, topics across a collection of articles. So document data is still record data. Rows or tuples and columns. But here, rows or, to say, documents, columns are words. And the values tells us or tell us how often those words appear. Hopefully that makes sense. Yeah. The next flavor is gonna be the transaction data. Okay. This is a special type of data, okay, where each record or row is a transaction. You see, each record is going to be a transaction here. We looked at this one before, right? And each transaction contains a set of items, and each transaction contains a set of items. For example, in grocery store, one customer, okay, shopping trip is a transaction, and the products they buy, okay, such as milk or whatever, bread, cook, milk, okay, are the items. Okay, so here's what actually looks like. See this? We got, I mean, the transaction ID here, and then items. Okay, look at the transaction one again. Okay, we have a bread, cook, let's say milk. All right, simple enough, right? Good. Um, though transactions again contains set of items, we can still represent them as record and data set because someone can say, well, how can does it matter? How can we do that? To have a set of items, how can you represent them as a record? Same structure, tuples and columns, right? Or rows and columns. We just need to reshape it, okay? And that's why this is often called market basket data, okay? Because each record really is just the content of a person's shopping basket. So what we can do with it? This format, okay, lets us find patterns like, for example, what items are often bought together. For example, look at the transaction of someone, yeah, we're gonna see when you get married, you have kids, yes, you're gonna buy milk, diapers, and you need to have, say, beer to have a balance, right? Anyway, so if someone, for example, buys diapers, okay, what else are they likely to buy? Beer, of course, right? association, you say, rules for product placement. So that's gonna help us to perform this kind of operation that you can perform this kind of data. Okay, yeah, that summarizes everything. I have a record data. I give you like the three different types of the data that can, oh, subtypes. Oh, type, yeah, subtypes. Okay, so let's move now to our second major category. The first one, record data. Second one can be the graph data, right? With the graph data, okay, the focus shifts, okay, instead of tuples and columns or rows and columns, we are now looking at relationships between entities. That's what I'm looking for. Okay. So here in this case, the entities become, say, nodes, okay, sometimes called vertex, okay, and the relationships between them are gonna be edges. So those are gonna be nodes here, and it's gonna be the edges, okay. And we have directed and let's say undirected edges, as we're gonna see later. Good. Um, we have got, I mean, three examples on this slide, okay. We talk about the genetic and molecule and web pages, okay. So let's walk through each one. So just very quick, just to give you an idea. So the first one is going to be, I mean, a generic graph. I've said genetic graph. It's generic graph, sorry. Okay. So generic graph, this is the abstract version. Okay. Nodes and edges that could represent anything depends on the context. Yeah. It can represent, as long as these nodes, we can use the nodes and edge to represent that. The entities, for example, they could be people, for example, objects, locations, concepts, whatever makes sense or makes sense for your problem. The relationships, okay, also flexible, okay? Friendship, for example, between people, connections between objects, relationships between concepts, and knowledgeable or knowledge graph, for example, whatever, okay? Yeah, we can talk about the social media as example, yeah, graph. Assume that we have a Facebook, okay, where people are nodes here, okay, and these connection edges can be the friendships, okay, are edges. Twitter, for example, the same, right? People are nodes, follows are edges. Transportation network, yes, we can do that. Cities can be our nodes here. Then, for example, the edges can be maybe flight routes, for example, or highways, whatever, right, in those cities or between these cities. Right? Um, we do have, I mean, oh, the second one is molecule, okay? That, I mean, here the entities are going to be atoms. Only difference, whatever the entities here, still we have to say entities and we have to say, oh, nodes, and we're going to have to say edges, right? So the entity here is going to be atoms and the relationship is going to be chemical bonds. That's all about this one. Okay? The third one is going to be web pages, okay? This one everywhere, right? The entities are web pages, every site, every page on the internet. The relationships are the hyperlinks, okay? Those clickable, let's say, links that take you from one page to another, okay? So the entire World Wide Web, okay? Massive graph, right? Billion of nodes, even more edges. Google built their business on this structure. So now let's look at some key properties of the graph data. Nodes. Pretty straightforward. Okay, they represent individual entities or objects in social networks. Nodes are people, in transportation nodes are cities, in the web nodes are web pages. Edges. Okay, these represent relationships or connections between nodes, friendships, bonds, links, whatever connect you or connects your entities. We do have the directed and indirected. Okay, here's where it gets interesting, right? Edges can be directed or undirected. Undirected, that means in this case, okay? So means the relationships goes what? Goes both ways. Facebook friendship, okay? If you are friends, okay, or if you are friends, okay, the connection runs both directions. So I have undirected line between friend, say people who are person one and person two. They are friends. Directed here, that means in this case, it can be one way, right? We talk about the direct, I'm self here, directed, right? Directed, that means the relationship can be only one way. Twitter follows, for example, I can follow you without you following me, right? That's directed edge. An arrow pointing from the follower to the followed. Hyperlinks on web page, Also directed, right? A page A can be linked to the page B without page B linking back. It's not required. Oh, if you're going to do that, that's fine, but it's not required. And we have weighted and unweighted, okay? Edges can be either can be weighted or unweighted, right? So what and say unweighted just means the edge exists or it doesn't. That's the only meaning here. You are either friends or you are not. Okay? Weighted, interestingly, gotta say what? Um, means we assign a number to that connection or to the connection itself. How many messages, for example, exchange? How strong is their friendship? Okay. How many times did someone click that link? Right. That way it captures to say the strength or frequency of the relationship, as we're gonna see later. So why does it matter? These properties matter because they determine what questions we can ask and what algorithms that we can use. Shortest path, for example, in a weighted graph is different from the unweighted, right? Certainty measures change with directed against undirected edges, okay? So the question here, what we can do with it, okay? What I can do with this data, okay? Graph data, let's ask answer questions like, who are the most connected people in a network? What is the shortest path between two nodes? How does information or disease spread through a population? Okay, bottom line, graph data, nodes are entities. To simplify the process, edges are relationships. And whether those edges are directed or weighted completely changes how we analyze the graph. Okay, now let's look at our final main category, order data. Order data sets. The attributes have a relationship, okay, involving order in time or space. The sequence, in other words, matters here. So we add more complexity, right? So remember, order data, okay, just means the attributes have relationships involving order in time or space. If you know that, that's perfect. And that's, I mean, the takeaway, at least with the slide. Now, one important example is sequential transaction data, okay? This is exactly like the regular transaction data we talked about earlier, market baskets, I mean receipts, okay? Items people buy, okay? Let me go back here. Similar to this, right? But, go back here. But there's a difference. It comes with an added superpower time. So we're gonna add the time. So it's regular transactions, data tells us what people bought together. Sequential transaction data tells us that plus when they bought it, in addition to whatever the regular transaction can tell us. And the time, I mean, information opens up to say two types of analysis. We have two different types of analysis we can perform because we have the time information. We have one thing is called to say time pace to say patterns. Okay, these are trends, okay, tied to specific time. Candy sales spikes, right? Let's say before Halloween, iced coffee sales jump in summer, gym membership, say, or membership surge in January, New Year resolutions, right? Yeah, that's what they're doing, people. Okay, so I didn't think anyway. So these are trends tied to specific times. I can do time. I mean, what's called? I mean, the time-based patterns. That means you can discover, let's say, trends tied to specific times. Okay, those things that happen when. The second here, we have sequential pattern. This is about what comes next. People who buy, for example, a new phone often buy a case within the next week. Someone buys a gaming console, then picks up, let's say, extra controllers on their next trip. Not in the same transaction, but in sequence over time. So see, the time can help us. Either going to find, for example, let's say, again, discover trends tied to specific times, or find what comes next. Okay? Um, when you say, I mean, in sequence over times for the sequential pattern, in the following days or weeks, right? So someone buys a phone, then buys a case on their next trip, and etc. Looks like I'm repeating myself. Okay. Let me show you what this looks like with actual data. I'm looking into this. Okay. Well, I've got to say 5 different times. We have T1 up T5. This is time, the customer, and this item purchase. If you just hide the time, we do have, the same structure that we had before, right here. Is a market basket data. Just we need to add the time here. So it's going to be changed to the sequence transaction data. Okay, back to this example. So we got up here 5 different types, T1 and T5. We do have to say 3 different customers, C1, C2, and C3 here. Good. And 5 different items, A, B, C, D, E, right? Yeah. On this table, or the top table, each row shows that here what items, we say, were purchased at particular time by each customer. Okay, what item purchased by each time, right? By, you say, but at a particular time, okay, by each customer. C1 at T1 purchases this one. Then C1 at T2 different time purchases those items. Okay? Yes. So look at this structure, okay? And we're going to see whether it's going to help us to useful for what type of analysis, whether it's going to be the time-based pattern or the sequential pattern. What do you think? So this structure is useful for time-based patterns or for the sequential patterns or for both. Can use this one in order to discover trends tied to a specific time or find what comes next. Okay, so let's start first, analyze this one at a time. Okay, you can pause the video first, then after that, think about the answer, then after that, see whether it's going to be similar to my answer or not. Okay, so this structure actually is useful for time-based patterns, right? Because they can tell exactly, for example, the trend tied to the specific time. If you give me whatever the time that we're looking for at specific time, T3, for example, I can tell you exactly what the trend tied to the specific time. For example, T2, I can find out all the customers that bought at T2 what they bought at this time. So you can discover the trend tied at that time. Look at the bottom table here. What we have here, same information, but organized differently, okay? Here, each row is a customer, okay? And that row contains all their transactions with the timestamp. So here you can organize the data, for example, what the customer gonna poach, okay? So here can give me, for example, more about the sequential pattern. Find what comes next. If the customer, for example, bought phone at the time one, the next trip to the store, he bought, for example, case for that iPhone, and etc. So I can find what comes next. Okay? So again, this structure is what we use for sequential patterns. Again, why? Because we can see each customer's journey over time. And what they bought first, what they come next, okay? What pattern emerged, okay? So I can summarize the following, okay? Here the key distinction between, the two tables that we have contains the same information, but I can use this one for different analysis, right? For the time analysis. For the time-based, say patterns, what happened at a specific moment, okay? Either tables works. Even this one can help me, the second one, right? But that's what can be much faster, easier to find the information that we're looking for. For the sequential patterns, okay, what comes next, okay? So that means we almost want the bottom structure. I would like to have that. Doesn't mean that it doesn't help, but that's gonna be much easier for me to work with. It groups any transactions by customer and keeps them in order. So we can say track sequence, right? Okay. The bottom line here, to summarize, the takeaway for this slide, sequential transaction data is just the raw material transactions with the timestamps. From it, we can find time-based patterns when things happen and sequential patterns, what happens next. Okay? Same transaction data we know, okay? Just with time added. And that small addition changed everything, especially when we organize it in the right way. So as what we did here. We're still in the order data, yes. But now let's look at another type, sequence data. Sequence data is what? I get a phone call, so I need to stop the recording. I got a phone call from my older brother, so I have to answer. By the way, again, we're still in the order data, right? We talk about the sequence data, and we define this one as what? As a collection of entities arranged in a specific order. Okay, like again, words or letters. Okay, but there's the key difference here. There is no timestamps, but there's order. So instead of time, what I'm gonna have to say position in an ordered sequence. Position one, position two, position three. The order matters, but there's no clock involved. There's no time. Classical example, genomic, say sequence data. Okay, DNA example sequence are just long strings of letters. You have A, C, G, T, right? In a specific order. So the sequence, for example, ATGC, for example, means something different from CGTA. You cannot change that. Position matters, but there is no timestamp. We don't ask when did this, you say, whatever feature appear. We ask what comes next in the sequence. Okay, so here's the difference from the sequential transaction data. Sequential transaction data, as we did the previous one here, is what? Has to say timestamps, real time between purchases. Sequence data, as we see here, has positions. Order matters, but time between steps isn't measured. Both are ordered data, just different flavors. Hopefully that makes sense, guys. Okay. Um, Now let's look at to see at another flavor of order data, spatial temporal data. Some types of data include spatial information, such as location coordinates, to say geographic areas, in addition to other attributes. I'm just focusing on this part. Doesn't mean that contains only these attributes. In addition to other attributes, you're going to have like a spatial information. Classical example, weather data, as we're going to see here. Okay, think about the precipitation, temperature, pressure, etc. These measurements are collected for lots of different geographical locations where matters. But here's where it gets interesting. Often these measurements are collected over time as well. So where matters first, at a certain time, that time as well, it's going to be collected over time, right? So you have got, for example, say temperature at location A on Monday, temperature at location A on Tuesday, and temperature at location B on Monday, and so on. Okay? So that spatial temporal data, space and time together. Okay? So what's this let us do? But you need to have this kind of information. With the spatial temporal data, again, we have a space and time together, we can ask, let's say, questions like, how does temperature change throughout, to say, the day at different locations? Is the storm moving east over time? How does air pollution spread across a city during rush hours, and etc.? Okay, we have many examples, by the way. We can have, for example, the GPS tracks from delivery trucks, location plus time, right? Satellite imagery over time, social media checks in with location and timestamp, disease spread mapping, etc. So spatial temporal data combines where and when, location and time together. And that's incredibly powerful for understanding how things move and change. Okay. Now we shift from the types of data to very practical reality, the data quality. Okay. You can pause the video for 2 minutes to relax, then you can start later. Okay? Continue, Emily. Not you. I mean, not me, actually. You. Okay. So here's the reality. Okay, we said we need to change from, let's say, very practical. Sorry. Now we shift from the types of data to a very practical reality, data quality. Here's the reality. Most of the time, we are not collecting data specifically for data mining. It's collected for other purposes. Transactions, say processing, customer records, sensors, whatever. And then we come along later trying to mine it for insights. So we don't collect that data for the data mining for other purposes. Okay. Um, that creates, challenges, okay? Because, the data wasn't designed for what we are trying to do with it, okay? So data mining has to deal with the detecting and correcting quality issues. There's the key, okay? We do this after the data is already collected, right? We cannot go back and fix the collections process and say, oh, after you collect the data, you try to mine the data and say, oh, you have to collect it again because I need to have the data has a specific feature. No, we cannot do that. We have to work with what we have got, right? So this means data mining focus on two things. First, detection and correction of data quality problems. We call this data cleaning, finding the issues and fixing what we can. That's the first one. Second, using algorithms that can tolerate poor data quality. Some algorithms are robust, they handle noise and errors better than others. When we can't fix the data, we need tools that can work around the problems, right? As we're going to see later. So why does poor data quality matter? Why we do care? Okay? Because bad data leads to bad decisions. That's the simple answer. Imagine a bank, let's say, building a model to predict who's, let's say, a loan risk. Okay? So if the historical data that we use or they use to train the model is full of errors, is poor, or missing values, the model will learn the wrong patterns. The consequences, they might deny loans for or to credit-worthy people, and even worse, give, let's say, loans to people who will eventually default. The business impact is huge, and it all stems from poor data quality. So the bank loses money and turns away good customers. Both sides of equations are broken. So this isn't just academic. Bad data costs companies real money and ruins customer relationships. So you should care. Um, we check first, do I'm still recording or not? Okay, I'm still good. Okay, now to tackle data quality, we need to ask ourselves three key questions. What kind of problems can we have? How can we detect them? And what can we do about them? We will answer these by looking at common issues like noise, outlier, missing values, and duplicates. Okay, let's start with the first data quality problem, noise. Noise in data is the random component of measurement error, values that deviate unpredictably from their true measurement. Can show up in two ways. For the object, okay, noise, say, means an extraneous object, an entire record that doesn't belong in the data set or something, you say, that shouldn't be there in the first place. Second, for attribute, noise means here, wait, yeah. For attributes, noise means a modification of original values. The object is real, but the value where recorded is off. So imagine that you are a store manager, okay? Tracking customer purchases. Most records are fine, but sometimes, you say, mistakes happen, right? One day, a record shows a purchase from a customer who doesn't exist. That is a noisy object. Another day, a real customer buys items totaling, you say, $25, but the system records $80, okay? That's a noisy attribute, okay? Someone can say, will it be like an error or whatever? Um, Outlier in this case, yes, we can say noise. You can think about the noise. It's going to be the overall randomness or error in the data. Later, as we're going to see, outlier, or that to say, is one visible instance of that noise, a single data point that doesn't fit the pattern. We're going to talk about that in the next slide. We experience this, right? A distorted, say, voice on a bad phone connection, or maybe during the online class, you're doing the Zoom, maybe they have distorted voice, right? Snow on an old TV screen, if you're old like me, the black and white dots in the screen, okay, random flickering pixels, making it hard to see the pictures, that old system I know. Or maybe you're gonna have maybe, for example, you're watching modern video streaming and you have a buffering, for example, as it gonna be YouTube or Netflix, that's gonna be like a noisy, right? Check out these figures here. These figures, we have three figures, right? Yeah. Show how adding random noise to a perfect sine wave distorts its shapes and magnitude. It's gonna help us to understand what's going on. Okay? Okay. On the left here, we have two clean sine waves, right? They have the same magnitude but different frequencies. Okay? This represents, a clean ideal signal with no errors. So everything is fine here. The second, or in the middle here, we combine these two waves, okay, together, okay, and the result is still a smooth signal, but a bit more complex, right? Importantly, it's still clean and structured. We can clearly see the pattern. On the right here, we take that same combined signal here, and what we add some noise. Now you can see the signal looks jagged and irregular. The random fluctuations make it harder to identify the original pattern. Okay, so this can, in general speaking, can obscure, the true underlying pattern we are trying to find here. Okay, so the key idea is that, okay, the noise distorts, the original signal's shape and magnitude, which makes pattern detections in data mining more difficult. So Monica said, okay, we talk about the data mining, why you have the sine waves here, what's the relationship? So now we're going to show you where the sine wave example becomes really useful, okay? Let me walk you through what's teach us about the data mining. This table will explain everything. So take a look at the first one here. In the sine wave example, we do have what? A clean sine wave, which going to represent here the true pattern that we actually want to discover. For example, customer behavior, sales trend, real relationships in the data, okay? And for the second row here, we talk about the wave combine, when you combine them together, which shows that in real life, multiple patterns interact. Seasonality plus, say, trend plus external factors all happening at once. The third one we talk about when you add the noise, right? This represents what happens in real world data collection. Errors, glitches, random fluctuations. This is the reality we deal with. The fourth row, or tuple here, we talk about the original wave distorted, right? That's the data we actually get, which the one we get something like this, okay? So the pattern is there, but it's hidden, right? Beneath noise. Now let's take a look at the key insight here. In the sine wave example, we know what the original wave looks like. We added the noise ourselves so we can know what we are trying to recover, right? But in the real data mining, we don't know, okay? We only get the distorted version and we have to figure out what the true pattern probably was. That's the whole challenge. Recovering the original wave in the sine example is exactly like our data mining goal. Find the true pattern despite the noise. Hopefully that makes sense. Bottom line, noise makes or masks, the underlying pattern. It makes everything harder to see, and our job is to find the signal hidden underneath. Make sense, guys? Noise is especially common when we are dealing with the spatial or temporal data with location or time component altogether, right? The good news here, when noise show up to say in space or time, we have some powerful tools. We can use techniques from, let's say, signal processing and image processing help to reduce, the noise and uncover the patterns that might, or let's say, otherwise be lost in the noise. So we have a way to try to recover from that. But the reality, noise elimination is frequently difficult. We cannot always clean it up perfectly. So much of the data mining, as we're going to see, algorithms, okay, focus on what? On something else. Building RAPs to say algorithms that produce acceptable results even when noise is possible. Bottom line here, we can almost remove noise completely. Okay, sorry, we cannot. So I wish we can. Yeah, we cannot always remove noise completely. Sometimes the best approach isn't cleaning the data. It's using algorithms that can handle the mess. Okay, so far so good. Okay, next outliers. Outliers are data objects or attribute values that are considerably different from the rest. So an outlier is either going to be one data object that's considerably different from the most other objects in your data set, of course. In this case, think about, to say, one person in the room full of 20 years old who's 85, like me and you guys. You're in the room now for 20 years old, maybe plus minus, yes. Yeah, plus minus. And the old guy, 85 years old, right? So I'm the outlier of this data set, right? Don't smile. I see you smiling back. Yeah. Or, as it can be data, object, sorry. Or it can be what? Values of an attribute that unusual compared to typical values for that attribute. Like, for example, we have 10,000 transactions on a credit card that usually sees 50 purchases or $50 purchases. Okay? Okay. Here's what gets interesting. Outliers actually play two completely different roles in data mining. So case one, outliers can be as, let's see, as noise. There are problems, okay? Errors, distortion, okay? They interfere with our analysis, and we need to clean them out to or work around them. That's what role the outlier play in data mining. The one that I don't like, and it can be as a noise, I need to remove it. If you are calculating the average income for a town, for example, a billionaire, for example, living there is an outlier, right? That will skew your result. I don't need this part to include it. You would probably want to remove them. Okay? The second case for the outlier is called as a goal. Okay? So sometimes the outlier are what we are looking for. That's what I'm looking for. I'm looking for the outlier. They are not noise in this analysis, in this case. They are signal. Okay? So classic example, for example, credit card fraud. The unusual, for example, 10,000 charge, right? For example, here. That's exactly what we want to catch. Intrusion detection here. What you're looking for. Okay? Unusual network activity might mean someone is hacking into a system. Disease outbreak, I know my mouse moves slow. Okay, a cluster of unusual symptoms, okay, could be the first sign of an epidemic. Understood. The question here, what causes outliers? Okay, sometimes it's like measurement error, okay, a sensor glitch, a typo, sometimes it's data entry error, someone's fat fingered and extra zeros, that might be typos, okay, measurement error. Other times it's gonna be like intentional error, right? Oh, let's say not intentional error. It's gonna be intentional, let's say fraud, yes. Fake transactions, bot activity. And sometimes it's just natural variation, okay? Generally, you say unusual but real events, a once in the decade storm, a one in a million customer, and etc. Or it could be a sampling problem. You just happen to capture a rare event in your data. And you took this one as a sample. Okay, here's the key insight here. The same data point can be noise in one context and the gold mine in another, right? It all depends on what you are looking for. So when you find an outlier, first question, is this a problem to fix or exactly what I came here to find? Right? If you know this answer, then you can find out whether you're going to remove it or this is the one that you're looking for. And we have this data set. We show you a few outliers. See, that's alone people that's sitting, yeah, far away. This problem is missing values. What's the missing values? are empty cells in your data set, right? The question here, why do values go missing? Okay, three bigger reasons here. The first one, information not collected. People decline to give their age, right? Weight or income survey questions to say left blank. If I ask you your age, can you give me your age? For example, if you ask me about my income, I'm not going to give you my income, okay, or my weight. I'm just kidding. But I mean, yeah, in other words, how does that make sense, right? Information not collected. People, decline to give whatever the answer or to share whatever the information that you're looking for. Second, not applicable. Okay, you wouldn't ask a child, for example, there's some questions that you are not going to ask a child or in your survey for their annual income, right? The attribute just doesn't apply. So in this case, it can be missing value. Third, it might be system errors, okay, or lost data. Okay, so in this case, system failure, for example, corrupted files, data that never made it into the database, and those, reasons why we're gonna mess. Data can be messed. Okay, I know it's a three reasons. I combine the third and the fourth one together. So generally speaking, you can say four reasons. Okay, to be accurate. Okay, so what we do, or what do we do about to say missing values? What we can do here? We have, here three main approaches, okay? The first one, eliminate. We can or just remove the tuple or rows or columns with the missing data. This works best, okay, when missing values are few and randomly distributed. Okay, you are not losing too much and you are not introducing bias. Okay, the second approach, I'm going to say estimate. I'm going to fill in the missing values, okay? We call this imputation. We got to look at this one later, okay? Oh, yeah, let's have a quick example here. If you look at the time series data, okay, like temperature reading, if a value is missing at 2 p.m., you might estimate it using the reading at 1 p.m. and 3 p.m., right? Average them out, and they're going to fill the blank. It might work, right? And the best way to handle the missing data, another way to say, okay, I'm going to ignore it. Some algorithms are built to handle missing values natively, okay? They just work around the gaps. When elimination or estimation isn't ideal, this is, the way to go, right? So here's the bottom line. How you handle missing values depends on why they are missing and what you are trying to do. There is no single, let's say, right answer, just trade-off, okay? Eliminate, estimate, or ignore. Choose based on your data and your goal in general. Okay. I need to double check the recording. Yes, still recording. Yeah, good. And yeah, what else? Next, duplicate data. Duplicates are data objects that are identical or nearly identical to one or another, right? Same record, same person, same transactions, showing up more than once, right? So how do duplicates happen? Okay, it's clear, right? That objects that are identical or nearly identical to one another. Okay. How do duplicates happen? Okay, the most commonly gonna be what? Merging data from different sources. The same person appears to say in your customer database, okay, your email list and your loyalty program. Now you merge them together, and now we have got the records for one person, right? Also common that we have what? Same person with different identifier, okay? For example, one record has john.smith at email.com, another has gsmith at email.com. Same person, different email. And the third is the data entry errors. Someone accidentally maybe hit submit twice and put activity, we can be have a fake accounts, spam submissions, creating duplicate entries. So dealing with the duplicates is a major part of data cleaning. We need to identify them and either merge or remove them to get an accurate picture of our data. However, the question at the bottom is important here. Okay? When should duplicate data not be removed? Think about it. Pause the video before jump to the next slide. So back to the question here. When should duplicate not be removed? Okay. And I call that this is the tricky part. Not every duplicate should be removed. Right? Let's be not all of them. Okay. Multiple transactions, example. Same customer buying items at different times. Those aren't duplicates. That's purchase history. Remove them and you lose the story. The second one, legitimate to say repeated measures. For example, same patient visiting the clinic multiple times, each visit is a real event, right? Not an error. Different people with similar names. John Smith in New York, maybe you have John Smith in Chicago, right? Look like duplicates, but they are two different people and intentional duplicates. Test that, for example, simulation control groups in experiments, you need them there, right? So that's fine in this case. Here's the key. Not everything that looks like a duplicate actually is one. So very important here, context matters. Your job is in data cleaning isn't just to remove duplicates. It's to figure out which repeats are legitimate and which are true duplicates that need to go. Now, we move from identifying problems to actively preparing the data. This is the data pre-processing. We will cover a set of core techniques used to transform raw data into a format that's more suitable and effective for mining. So we're going to look at all of them. Let's start with the first one, aggregation. Aggregation is the process of combining two or more attributes or objects into one. We do this for several reasons. First, for data reduction, it's easier to analyze monthly sales totals than millions of individual transactions. Second, change the scale. We can analyze data at the store level to the city, state, and even country, okay, level. And third, aggregated data tends to be more stable with less variability. Okay, for example, daily sales can fluctuate a lot, but monthly averages, say, provide a smoother and more reliable view, right? So now looks at this table of customer purchases. Each row represents a single item within a transaction. For example, transaction 10, 11, 23 appears twice, right? One for watch, second for battery, right? Both purchased in Chicago on the same date. So even though it's one shopping trip, it's recorded as multiple rows because each item is listed separately. So over time, this creates a very large and detailed data set. To simplify this, we can apply aggregation. For example, we can group all items purchased on Chicago on, let's say, 090604 24, right? Let's say September 6, 24, okay, and summarize them into a single record, such as the total sales or total number of items sold and etc. Okay, more generally, imagine tracking sales across many store locations over an entire year. Instead of storing every individual transaction, we group transactions by store and by day and say summarize them. This means that instead of thousands of detailed records, we end up with one record per store per day. This makes the dataset smaller, easier to analyze, and more useful for identifying patterns like daily sales trend per store, rather than, say, focusing on individual item level details. Okay, so when your data feels too nosy, right, or too detailed, ask, can I aggregate this? What is the right scale for what I'm trying to see, right? Okay. Um, Sampling means selecting a subset of data objects for analysis, right? It's a primary technique for data reduction, and it's used everywhere, right? For both initial exploration and final analysis. Okay, so why sample? Now here's something interesting. So why we sample in data mining is often different from why we sample in statistics. So in statistics, okay, the motivation is usually what? Data collection. Getting data on everyone is expensive or time consuming, so you sample because you cannot get all the data, right? In data mining, the situation is different. The data is already available, right? You have got, let's say, you got it, right? You could process it all, okay? But here's the catch. Processing the entire data set might be too costly or, you say, uh, too slow, right? So here's the key difference to summarize that. Statistics, I mean, sample because you cannot get all the data. For the data mining, we sample because you don't want to process all the data, okay? So if you think about an example, very quick example, you have 10 years of customer transactions, okay? Billions of tuples or rows. If you try to process every single row for a quick, let's say, trend analysis, it might take hours or maybe days, right? But a well-chosen sample, it can give you, for example, 95% of the insight in the, let's say, 5% of the time, okay? So the bottom line in data mining sampling isn't about affordability of collections, it's about affordability of computations. Okay? So work smarter, not harder. Sometimes a sample tells you, for example, everything that you need to know without the weight. Okay? Okay. Just double check that, confirm that I'm still recording because sometimes it's suddenly stop recording. Okay, for non-news. They say sampling only works if you do it right, right? You have to do it in the right way. So here's the key principle. Using sample would work almost as well as using the entire data set if the sample is representative. So what do you mean by representative? Okay. A sample is representative, okay, if it has approximately the same properties as the original data set. Same patterns, same distribution, same relationships. Okay. So our goal here is what? Is to capture the essence of all the full data set without the cost of processing it all. Bottom line, a good sample isn't just smaller, okay? It's capture the characteristics of the whole data set. So it's not only the size, as long as you're gonna capture the characteristics of the entire data set. Okay? So let's look at the types of sampling. Okay. So first, we have, simple random sampling here. Every item has an equal probability of being selected. Okay, we have two flavors here. Um, the first one without replacement. Okay, so that means in this case, once an item is selected, it's removed from the population. So each item appears at most once. This makes sense, right? Sampling without, oh, sorry, with replacement in this case. Okay, so items aren't removed. Okay, the same object can be picked more than once, like drawing, let's say, names from, let's say, a hat and putting each name back after drawing. So the first one is going to be simple random sampling. The second flavor is stratified sampling. Okay, this one's important when your data has meaningful subgroups. You split the data, okay, into partitions called strata, okay, based on something important, age groups, for example, regions, product categories. Then you draw a random sample from each partition. Why? Because it ensures to say each subgroup is adequate. Is properly represented. Okay, if you just add random sampling, you might accidentally leave out to say a small but important group, right? So when to use each? Use simple random, okay, when your population is uniform. Use stratified when subgroups matter. So once you have picked your technique, how many do you actually sample? Which is going to be the next question. What the sample size is going to be? Straight up, okay? So large samples, okay, are more representative. They capture the data picture, but they are also, let's say, dimensioning the sampling advantage. If you sample 90% of the data, you are almost back to processing the whole thing slower, costlier. Okay? Smaller sample size or samples here are faster, but risky. You might miss patterns entirely, or worse, detect, patterns that aren't really there. So you end up you have like a false positive from not enough data, right? So the goal here can be what? Is finding the sweet spot. Big enough to capture the patterns you need, small enough to be efficient. So the bottom line, the sample size is balancing act. Too small and you miss the story, too large and you lose the point of sampling. So I need to have to be, find the sweet spot, the balance between. So finally, let's talk about the risk of sampling, okay? Loss of information. So look at this example, okay? So we start with, the data set with 8,000 points. That's the given data set in the left, okay? So look at this example as with a sample of 2,000 points. Most of the structure, okay, from the original data set, which used to be 8,000, right, is still there. You can still see the pattern. So it's not good, bad, right? Good. But when you sample of 5 points from the original data set, much of the structure is going to be what is missing. The patterns disappear. What's left might not represent reality at all. So now we lose. Yeah, we sample data, but we're going to lose, the pattern. Okay. So here's the thing. Let's say the key insight. A sample that's too small doesn't just shrink your data, it changes let's say, it changes your data. Okay. The patterns you see in tiny sample might not be the patterns that are actually there. So sampling is powerful, but only when you get the size right. Big enough to keep, the structure, small enough to keep the advantage. Okay. And next up, discretization. Okay. Discretization is what? It's the process of converting, let's say, a continuous attributes into categorical attributes. So we're going to convert from what? From continuous attributes into categorical attributes. We take a potentially infinite numbers of, let's say, infinite number of values, like ages from 0 to 100, and map them into small number of categories, like a child, adult, senior, right? Okay, so the question here, why do we do this? Because some data mining algorithms requires categorical data. They cannot handle continuous numbers directly. Classification algorithms, association analysis, they need categories. So we have to map them through discretization. Okay? Yeah. So discretization, involves, to say, two decisions. Okay? First, how many categories? 3 age groups, for example, 5, 10. Second, how to map the values. Okay, where do we say draw the boundaries? For example, is 18 is the cutoff for adults, 21, for example, 65 for seniors. So yeah, you need to specify where, how to gonna map the values. Okay, bottom line, discretization turns to say continuous numbers into meaningful categories for algorithms that need them. Okay, and that's the takeaway. Good. Um, Discretization comes in two flavors, okay? Unsupervised and supervised. So we need to understand the meaning, what the difference between them. Start with unsupervised discretization. Means partitioning the data without looking at any class labels. You are just looking at the distribution of the values themselves. Where are the natural gaps? Where does the data cluster, and etc. Supervised discretization use class labels to guide where you put, the boundaries, okay? You want intervals that are pure, okay, where most of the points in each bin, okay, belongs to the same class. So when you use each of them, use unsupervised, okay, when you are exploring or don't have labels, use supervised for classification tasks where accuracy matters. And you do have class label. Okay? So the key insight here, supervised discretization, okay, usually produces, let's say, better results for classifications because it uses the target to guide the boundaries. Okay? Let's look at the three common unsupervised discretization methods. Okay? So equal width, okay, that splits, the range into equal size interval, okay? So simple, but can create empty pins if data isn't even, they say, evenly distributed, right? Yes. Equal frequency puts roughly the same number of points in each pin, okay? Ensures balancing categories, but boundaries might fall in the middle of dense cluster. K means uses clustering to find natural grouping in the data. It's more sophisticated. It's fine to say where the data actually clumps together. Okay. I'm going to show you the figures, okay, which show the same data discretized with each method. We're going to see how the boundaries fall in different places, as we're going to see in the next slide. But first, let's go with the bottom line. No single best method. It depends on your data and what you are trying to capture. So it depends which one you're going to use. Okay, let's start with this example. So here we'll look at the one-dimensional data set. We have added a random Y component. Just so you can see, the points more clearly, okay? If you have in one direction, for example, yeah, I think I lost the connection here. Let me try if we can connect to my tablet. And try to, yeah, 1 second. So yeah, I managed to connect, right? Yes, good. So assume that's what we have. We do have the points here in our slide. We end up, we have what? To say that's what we have, right? We have points from 0, 5 to say 10, 15, and 20. We have two outliers, one at the 20 point here, let's write this one, and we have at the 0, right, two outliers. Then we have many points at 5. We have more than 1 point, the blue one. If you take a look here, we have many points. All of them is going to be mapping on the same, let's say, line or same value. For example, we have assume that we have 20 points, okay, or values of x. All of them are 5 on this range. So again, mapping in the top of each other, right? So that's what you have. Good. The problem here, when you visualize what's called to say one-dimensional data, multiple points may have the same or very similar x values, causing them to be overlap and hide the pattern, right? So example, here I think the blue one, I'm bad with the colors, so try to get this color. I believe this one, maybe. All of them have 10 here. Then we have the third one gonna be the yellow, yes. And here the fourth one gonna be the red one. Oh, that's easy to write. I believe, yeah, that's whatever. So yeah, there's whatever the values that we have. Okay. So in this case, it's one dimensional, right? You cannot see the pattern. So how can you fix that? To address this, well, I'm going to add a small random variation to the y-axis, which can be spread points vertically. For example, for every single point in x, I'm going to add a random value of y. So here it's going to be what? So the value is going to be what spread in the vertically. So here you have to see the points like this. Now we can see the pattern. And that's what we did here. Stop share and back to the slides. And that's what we did. Okay. The random value or y values, okay, are only for visualization purposes. They spread them in the points vertically so we can see the following. I can see the clusters now. I can see the gaps. The empty space between the clusters, okay, becomes visible, right? And I can see the outliers. Now we have two outliers. So we have two outliers. We have a data set points between 5 and 15. Good. So that's the given data. Good. This is the discretization, okay? The simplest method, or the simple method that we can use equal interval width. So what we're going to do in this case, I'm going to divide the range of the data into 4 intervals. For example, we need to have 4 let's say, ranges or 4 intervals. Okay, so I can divide the data from 0 up to 5, from 6 up to 10, from 11, for example, up to 14, 15, from 16 up to 20. And that's the range that I have, right? Good. All of them can be equal size. As you can see, this method, you say, works poorly in that case. The outlier at 0 and 20 can be stretched, the interval uneven. Okay, so for example, it might be in this case, one interval is going to be almost empty, right? Maybe another get merged with points from two or more different natural, let's say, groups. So in this interval, we have one from the blue, one from this green. I know, um, blue, light blue, and from, let's say, yellow. So three orange can be mixed here, right? So some of them probably almost going to be empty. Some can be, for example, from here we have most empty. We don't have a lot of that. Here we mix more than one interval together. Or they mix point from different groups, which is bad. Okay. So this method can be highly sensitive to the outliers and can fail to reveal the true distribution and natural grouping of the data. So that's bad. The next one, we're going to use to say the equal frequency. That's what we used here. So here we create pins. Okay, we have 1, 2, 3, 4 pins, right? So that each pin, okay, contains approximately, you say, the same number of points. So the same number of points here, the same number of points here, the same number of points here, the same number of points in this pin. Okay, this solves the outlier problem. But as you can see, it can be fooled by the natural distribution of the data. Okay, to get our 4 pins, for example, with equal counts, it has to cut through to say the middle of 2 or say more of our natural groups. So I have to cut from here, I have to cut here, so that's gonna be maybe you cut more. So actually here we cut actually among only 2, right? Yeah, we cut only through 2 middle value. Through the middle of 2 to say our natural groups, yes. But at some point from group 2, for example, here, and group 3 together, example, or group 1 and group 2 together, right, into the same pen. So that's not good solution. Okay. A more intelligent method is to use clustering techniques like k-means and k equal to 4 in this case. Here we are what? Here we are not just pinning, based on symbol rules, okay? We're actually trying to find the natural grouping in the data. So as you can see here, k-means does an excellent job. Okay, if you see that, you have 1, 2, 3, 4, and here you can clearly see, the boundaries. Okay, and the k-means places the pin boundaries exactly where the gap are between our natural groups. There's a gap here, see the boundary and the boundary. So that's perfect. This is much better and supervised approach. Hopefully that helped us to imagine that. We'll try to do that in the maybe next week using the Python. Still, we need to finish this chapter. Then after that, maybe have some practice using some Python code, which help us in order to see how to work. How can we understand that? How can we visualize that? How do you write some Python code which allow us to perform these such operations? And we can visualize them. Okay. Now let's look at the supervised discretization. Okay. Where we actually do what? Use the class label to guide our boundaries. That's supervised, right? So when you let's say perform a classification and the class labels are known for some data objects, discretization methods that take class labels into account often produce better results, which makes sense. Okay, and the reason is clear, right? Because we can play split, okay, to maximize, you say, purity, meaning each interval contains mostly one class label. That's what mean when you say maximize the purity. Make it pure, again, meaning each interval or each pin contains mostly one class label. Okay, and this is where entropy comes in. Okay, we're going to look at entropy later in detail, but feel just we need to measure that. Entropy, measures, say, the uncertainty or disorder, right? If you remember that, from other classes, we cover, you should somehow cover the entropy, okay? So we have a low entropy, that means in this case, a pure, most points in an interval belongs to the same class. If we have high entropy, that means mixed classes are all mixed together. So that's the one that we don't like. So here's very quick. I'll give you an overview how entropy-based discretization, works. Okay. So we evaluate, say, the potential partitions by calculation of their entropy. The goal here to minimize the entropy. Okay. And then create intervals that are as homogeneous as possible with respect to the class label. Okay. Yeah, I don't want to go over that in details. So that's enough in this case. Yeah. Okay. Um, so now let's compare the two main approaches to discretization. We have another approach actually. The next one. We do have the top-down and bottom-up, those other discretization algorithms approach actually. Sorry. So here's how they work. Okay. We have a top-down. That depends on the way that you're gonna start. Okay. So again, those are the two main approaches to discretization. Okay, the top-down starts with the full range. Okay, find the best split points, divides into, let's say, two intervals, and recursively repeat. So start with the full range. All of them is gonna be in the same interval. Then you start dividing. Okay, it looks like if you think about the UML diagram that we cover in the database class is 425. Remember when they teach you the extended ER model, they said we have specialization and generalizations. You can start from the top, then you have the more specific, and you start from the bottom and you make it more general, right? This is, from the top bottom. Okay? Specialization, if you think about it. That's the top down. Now, something similar. The structure doesn't mean that it's going to be the exact thing. The second one, bottom up. That means in this case, you're going to start with each, let's say, distinct value at its own interval, then find similar neighbors, then start merging them. Repeat until done. So starting from unique values, then make it, start getting, merge them until you're done. It can be top down or it can be bottom up. Those are the algorithms and how can you perform. So you have top down and bottom up. Those are the two approaches, and each of them can be unsupervised or supervised. It depends what you try to perform. So unsupervised examples, top down can use, for example, equal width and equal frequency. Bottom up, okay, based measures, based on how close values are, no class label needed. That's unsupervised. Okay. So again, the top down has equal width and equal frequency. They can use for the bottom up. You can use what in this case? You're gonna use, merge based on, let's say, how close values are. So no class labels needed because it can be unsupervised. Good. For the supervised method or examples, top down, it can use, for example, the entropy-based splitting. It uses class labels to maximize purity. Bottom up, it can use chi-merge or chi-merge. It uses the class labels to guide which merge help classifications. So here's the key. Top down against the bottom up is about direction. Okay, splitting versus merging. Supervised against unsupervised is about whether you can use the class labels or not. Make sense? Hopefully that helps us in order to distinguish between them. So these are independent choice. Okay, you can have all four combinations if you want. So bottom line, don't confuse direction with supervision. Okay. For combinations, all valid, choose based on your data and what you are trying to achieve. Next, binarization. Okay. Binarization maps a continuous or categorical attributes into one or more binary variables, just zeros and ones. Okay. So we have to start with the first method. Here's one approach. It's called binary encoding. So in this case, if you have m categorical values, first assign each to an integer from 0 to m minus 1, then convert each integer to binary. And you need how many bits? So you can compute that following. Use n equal how many bits that you need in order to represent all the attributes or the values that you have, all the binary values. Okay, you need to find out how many digits, how many bits. Sorry. So you can use ceiling log to n, okay, which is find out how many binary digits. So again, you will need in this case here n equal log to n using ceiling binary digits, which is going to help us. That becomes your new binary attributes. So let's have example this table. Okay. So if you take a look here, we have 5 categories. 1, 2, 3, 4, 5. Okay. So overall, let's see for okay, good, and great. I need to convert that into, let's say, map them to, let's say, what? Remember, to the an integer from 0 to n, right? So the value of m is equal 5, so I can map this one from 0 up to 4. So I assume there'll be 0, 1, 2, 3, 4. How can you represent the 0, 1, 2, 3, 4? I will take the value of m, so I look to the power, to m, sorry, ceiling a bit, I believe 2.3 something. So ceiling, that means in this case, we need 3 binary attributes, x1, x2, and x3. Okay, so again, x1, x2, and 3 is going to be how many binary attributes that I need, how many bits I need to represent all the values that we have. All right, so you can start all of them 0, 1, 2, 3, 4, and etc. Right? The only thing that I don't like here, take a look at the good here. You see that here, good is represented as 0, 1, 1. That means in this case, both x2 and x3 is going to be equal to 1, right? So, and that creates a problem because good uses to say both x2 and x3. These two attributes become, to say, correlated. We have accidentally created a relationship that wasn't there before. So that's not good thing. So what we need to do here? The method theory for association analysis, we have a different requirement, okay? Association needs a symmetric binary attribute, okay? Where only the presence value equal to 1 matters. The zeros doesn't count or don't count, okay? The solution, we're going to use something that's called one-hot encoding. We create one binary attribute for each categorical value, okay? So take a look at this table, okay? The table shows this. 5 categories, the same categories that we have. 5 binary attributes, because for each of them you need to have like an attribute, right? So we're going to have 5 binary attributes for all, okay? For example, it's going to be only x1, 2, 3, 4, 5, since we have 5, because each of them have equal, only value 1. So if you have 6, that means you have 6, say, binary attribute. If you have a 10 categorical value, that means we're going to end up, we have 10, let's say, binary attributes. So I have 1, 2, 3, 4 binary attributes. Okay. So here for the alpha, it's going to be the value is going to be equal to 1x1. For the pool, it's going to be x2 equal 1. And so we solve the problem, right? There's no correlation, no unintended relationship. So that works fine in this case. Okay. So which one to use? Binary encoding, okay, is more compact, fewer attributes, but can create a correlation. One-hot encoding avoids correlations, but creates more attributes, right? So binary encoding is fine for general data mining. One-hot encoding is essential for association analysis. So it depends, okay? Bottom line, choose your binarization, okay? A method based on your goal, compactness, or let's say against independence trade-off matter in this case. So next up is going to be attribute transformations, okay? So I believe I'm going to stop here. So we're going to do that in the next week during our normal lecture. Okay, thanks, guys, and enjoy the rest of the weekend and see you on Tuesday. Have a nice day, guys.